koutou, and welcome on to the Centre for Sustainability, ko Caroline Orchiston Tokuingon. And today it's a real pleasure to introduce you to Michael Palin, or Mike Palin, from over in the Geology department. Mike's a geochemist, and today he's going to be sharing some pretty innovative and exciting thoughts on greenhouse rock and how geologists can stop global warming. I'm really excited to hear more about it. So welcome, Mike.
Thank you, and thank you everyone for coming. Thanks to the Center for accepting my talk. And the title is intentionally provocative, and that's why I'm here, is to provoke thought and consideration of some factors. Okay, so I always get bound up in the introduction of talks and then have to rush through everything at the last 10 minutes. So I'm going to rush through the beginning of the talk so we get to the good stuff. Okay, so here's the organization scheme of the talk today. And I originally gave this, well, I've been thinking about it for a long time, and other people have also, and but I really kind of finally put it together last year around Easter time, and it just seemed so appropriate to frame it in these three chapters. So we're going to start with the Garden of Eden, move on to hydrocarbon hell, and eventual salvation. Again, remember, this is meant to be provocative, so if you're being provoked, I'm doing my job. Earth's place is special. We all know this. We're lucky. We live in the habitable zone. If you don't know what the habitable zone is, it's the location around a star where a planet is located, where if the wide variety of additional factors converge, you can have liquid water stable at the planet's surface. And the reason that astronomers refer to this as being habitable is that we think, or they think, that water is a pretty essential component for life to exist. And so when you look out at exoplanets, you're trying to assess, well, if you have a planet that's within the habitable zone, what other factors would you look at, et cetera, et cetera. So we're in our habitable zone for our particular star here. And of course, the rest of the planets in the solar system aren't. Now, that doesn't mean that there can't be transient liquid water present at the surface, as we think in the case of Mars, but we're here. And that means that we live on a planet that is blessed with the three phases of water. We have abundant liquid, the oceans, water droplets in the atmosphere, we have water vapor in the atmosphere, and of course we have ice. So we have a special place. Now, it's important to point out that we're actually on the fringes of our habitable zone, especially in the past when our sun was not as strong as it is today. And we need a greenhouse. Otherwise, we'd be frozen. We'd be a frozen world. And the way the greenhouse works is not, a greenhouse atmosphere works is not like the greenhouse that is in your backyard. It is an unfortunate use of terminology, but we're stuck with it, so let's just live with it. A greenhouse atmosphere effectively traps heat. When a planet is in radiative equilibria, the energy that it emits to space is equal to the energy that it receives incoming. Yes, there's a little bit of ground energy stored in the interior of the Earth, but it's really not important. Now, the question is how does that energy get out? If you have a planet that is a smooth black surface, it won't have any greenhouse effect, and the planet's surface will be, depending on where the position is relative to its star, may heat up a little bit, but there will be a small temperature difference there. We have an atmosphere, and it's good, And the important thing here is that our atmosphere allows radiation from the sun, which is firmly in the UV part of the spectrum, to penetrate. It gets a certain amount of it reflects, a certain amount of it is absorbed. Some of it is absorbed by the surface. That which is absorbed by the atmosphere and the surface re-radiates depending on that temperature, but that temperature is much lower than the sun is, so it doesn't re-emit in the UV, it re-emits in the IR. IR is great because it gets absorbed by molecules in the atmosphere that contain 3 or more atoms. And those bonds can absorb IR radiation and re-emit it. The important part of all this, for our purposes, is that when it's re-emitted by a molecule in the atmosphere, that re-emitted energy can go in any direction. It's not forced to go out. It can be re-emitted down to either the lower parts of the atmosphere or the surface, and the process starts over again. That has the tendency of heating the atmosphere depending on how thick it is, and the surface as a consequence. And well, that's pretty fascinating there, Ian. That's a little bit embedded video that did get quite embedded. We got the audio, but not the video. That's Ian Stewart. You can look it up on YouTube. He's a fantastic, he's a geologist. He's a fantastic speaker. He talks about lots of different things, but just look up about how a greenhouse effect works, and he has a nice little simulation there that I've tried myself, and I haven't quite gotten it to work yet, but that's because I'm cheap on the old IR camera bit. Okay, so here's what I just said. We get radiation in from the sun, it's in the UV. It gets cut out by certain atmospheric gases. What gets re-emitted from the surface in those gases is at a lower temperature, therefore it's at a longer wavelength. And you can see these are continua. That would ordinarily be the case, but they have lights taken out of them by absorption of our different types of gases. And the things that we're interested in terms of the atmosphere, of course, is water vapor. It's controlled by those 3 phases: vapor, liquid, and solid. So it's constantly transferring, and it has a rapid change of response time. These guys, carbon dioxide and methane, are the major species of the atmosphere that are longer lived, and they can build up. And in fact, that's been to our great advantage over our history as a planet. And geologists know this really well, which is why the vast majority of us are really, really concerned about the experiment that we're running on planet Earth right now. What we know is we can go and look at our geologic past records, sediments built up over millions of years, and a variety of fossils, and we can trace them: warm species, cold species, different kinds of sediments over Earth history. So this is time going back. And these are a variety of different proxies: leaf shape, isotopic composition of carbonate fossils, records of glaciation, scratched rock, buildup of moraines and drop stones and sediments, et cetera, et cetera, et cetera. And what we have been able to build up is a record of atmospheric CO2 concentrations and a variety of other temperature measures. These are the most extreme times in the past when there have been large glacial sheets. And of course, we live in a glacial interglacial shifting age now. For the last 35 million years or so, there have been several other big episodes in Earth history. We can even go back further, in a time when Earth was completely covered by ice at least twice. Believe it or not, just shows us how much on the edge we are with regard to the habitable zone. But what we know is that there's a first order relationship coupling, at least in terms of the record, and we'll get to why that is in just a moment, between surface temperature and CO2 in the atmosphere. So when CO2 goes up, the surface temperature warms up. Okay, this is all because of the carbon cycle, as it turns out. let's review where our carbon is today. Well, you can break it down into a couple boxes. Atmosphere pre-industrial, don't worry about these units, they're big. They're 10 to the 15th grams of carbon. The atmosphere and veg cover of Earth about equal. They are in rapid equilibrium with each other, exchanging carbon. Vegetation dies, adds carbon to soil. Soils also have independent microorganisms and things, and older carbon in soils. To a first approximation, atmosphere equals veg, veg plus atmosphere equals soils. Next, and they are in a little bit of a slower equilibrium and transfer. The uppermost parts of the ocean, again, probably about equal to each of those individually, roughly speaking. A little bit slower in terms of the transfer rates. And then we have the deep ocean, which is much further out of communication, but also whose size of carbon reservoir is much larger. And that's going to be the general theme of how this works, is the bigger the reservoir, the further it is away from exchanging its carbon rapidly with the atmosphere. And then finally, we get into the kind of geologic realm, sediments and rocks of the crust. We're going to leave the mantle out of it because that's really slow and we don't really know that much, but it's huge, okay? And it's on long time scales. This is the dog that wags this tail. On shorter time scales, it will be smaller portions of it, okay? This is slow, but it's nonetheless very important over long time spans. So how does it work? It does exchange eventually with the atmosphere, and the way it does that is over something called the carbonate silicate cycle. And the way it works is you take a rock bit, rock contains minerals. Those minerals include elements that form cations that will leach into water when the rock undergoes chemical weathering at Earth's surface. Those elements get transferred into the ocean, which is in the shallow part in equilibrium with atmospheric CO2, and those dissolved elements that have been leached out of the weathered rock will combine with the CO2 and make solid carbonate. Life in the oceans takes advantage of this now. Before there were carbonate secreting organisms in the ocean, there were other mechanisms to do this. This has been going on for as long as Earth's surface has had liquid water that allows rock to be chemically weathered and leaching these elements into the ocean where atmospheric CO2 dissolves and they precipitate shells. Now, if it was a one-way track, we would be like Mars. We would be an ice house, but we're not. Even in the middle of winter on a nasty Dunedin morning, we are not Mars' surface. We're warm. And the reason is that this geologic reservoir of carbon slowly gets transferred back into the atmosphere. You remember I mentioned that there was a time 600 to 700 million years ago when Earth's surface from poles to equator was covered by ice. Call that snowball Earth. And the reason that we, Earth, got out of that fix at that time, this weathering cycle had operated too well and had drawn down CO2 so low that the greenhouse effect was small. Once ice starts building up and getting close to the equator, there's a runaway effect because it reflects light. But Earth, the interior of Earth, still operated due to its internal heat. We won't say why that internal heat is there. Anyway, it drives geologic processes that take this sediment and release the chemically bound CO2 back into the atmosphere and make new rocks composed of those same elements that will undergo the cycle again. Okay, and this has been going on for, well, at least 4 billion years on our surface, perhaps even longer ago than that. How do we know? Because those are the age of the oldest carbonate sedimentary rocks that we have. So here's a little bit of a, oh no, it's a chemical equation. No, it isn't, don't worry about it. Okay, here's some of the geology. If you want to know about that, just look up plate tectonics. It's what makes our planet so dynamic. So we have this carbonate silicate cycle where the silicate rocks at high temperature fight with the carbonates at low temperature. Two processes, chemical weathering and then the reverse at high temperature, these things called metamorphism and volcanism. They fight over who gets the calcium and magnesium. And there's a balance. It's there as a reservoir to get broken down when our atmosphere gets a little bit depleted. And when the atmosphere gets enriched, those weathering reactions take place are faster at higher temperatures. So this is our analog. Earth does this. It just does it slowly, but that's okay. There's lots and lots of evidence for it, and we'll get into that in just a minute. So that's our Eden. Everything's hunky-dory. We're the right distance from the sun. We got liquid water. We have plate tectonics. Everybody's happy. Sometimes we get a little iced over. Sometimes we get a little overheated, but it all comes back to equilibrium on 100 million year time scales. Until this. Humans are so clever. We are very, very clever. We like to burn things. I don't know, we're just all like teenage boys. I'm not exactly sure. Yeah, and so when we run out of wood, we find other things to burn. Whale oil, rock oil, petroleum, a special kind of oil. Coal, gas, so all those beautiful things. And so what we do is, here we are, this is just the last couple, 1,500 years or so. We're happy burning trees and living in mud huts and having a few empires here and there and black plagues and all that kind of stuff. And then we get really clever with life and we discover coal. Coal is just a magnificent heat source when you consume it amazingly. Okay, this is an ice core record. How do we know what things used to be? Well, one of the records that we have available to us over the last million years or so is ice formation in polar regions. And there are cores from Antarctica, from Greenland, and they show a kind of a bouncing around a little bit. This is, of course, all in our latest interglacial stage, where we're at about 280 parts per million in the atmosphere. Now we're well above 400. This is an old slide. So we're up there in the attic someplace now. And there's a region of overlap, so there's no problems. And this is called the hockey stick, and it's a good thing, not a bad thing. No, it's a really bad thing, but it's good that we can figure out these kind of things and have the records that we can. This is meant for a broad audience, and I know I don't have to convince anybody here of the source of this, but I'll just bring it up because I have prepared this for a variety of audiences, some of which may be less amenable. Okay. Are we really sure the CO2 that has built up that into that hockey stick, whichever way you hold it, that it's coming from fossil fuels or combustion? And the answer is yes. Yes, we know that a couple ways. Here is the record of CO2 increasing in the atmosphere. And again, these are old graphs. There's a couple things that we can compare that to. One is the atmospheric oxygen concentration. It's actually gone down a bit. Don't stress too much. It's gone down really tiny bit, and there's lots of oxygen in the atmosphere, so there's no, but it has measurably gone down. And the amount that it's gone down is pretty much exactly what you'd expect for that simple chemical reaction. You take carbon and you oxidize it, combust it, and make CO2. There's another record, more geochemical. The carbon isotopic ratio, stable isotopic ratio, 2 stable isotopes of carbon. The major one is carbon 12. There's a minor one, carbon 13. And it turns out that the carbon 13 to 12 ratio has gone down, which is consistent with incorporation of excess carbon 12. That's exactly the kind of carbon that is in fossil fuels. It's not the kind of carbon you get out of the mantle when you make a volcano. So it's not hidden volcanoes on the ocean floor that's causing CO2 to rise, okay? It's not lizard people. It's us burning fossil fuels, pure and simple, just end of. And we are so efficient at doing this. How efficient are we? This is a ballpark, okay? You don't have to worry about the 200, just remember hundreds. All you need to know is in the last couple hundred years, more or less, we're just burning all this naturally sequestered organic carbon in the form of coal, oil, and a little bit of natural gas that had accumulated over the previous 200 million years, plus or minus. That's a factor of a million. Now, we can argue about factors of 2, we can argue about factors of 10. You're not going to get away from the fact that we are putting prodigious amounts of naturally sequestered organic carbon, that's another part of the carbon cycle that we're not going to talk about, into the atmosphere as a burst. And there's natural analogs for this, and bad things happen, but anyway, that's just the facts, Jack. So, here's another old slide from another unattributed source. Anyway, don't worry about this. These are these big numbers. Don't worry about it too much. The important thing in here is that we burn. We also have land use changes, but those are like only 10% or less of the total issue. There's no doubt this is the #1 issue. The good news is about half of what we burn, Earth takes care of. Half. It wants to help. It really is doing its best. It's huffing and puffing to keep up with us. About half of it, and about half of that again is put in the ocean. And it's true. CO2 is plant food. Okay, you hear this all the time. Oh, it's plant food, so don't have to worry. Yes, we still have to worry, because half of it isn't getting sequestered. We call that ratio of what gets into the atmosphere relative to the emissions. So here's an emissions trajectory over time. And if it looks like it's taking off on an exponential, that's exactly right. Yes, there are divots. There are economic downturns. There are oil crises, which are actually really, really good. There are pandemics. Those are good too. And then there's the net gets in the atmosphere. And this red line that I've highlighted here is the so-called airborne fraction. It's about 50%. About 50% of what we burn stays in the atmosphere, the rest. That is a disconcertingly constant amount, since as far back as we can reasonably estimate or even kind of guesstimate with regard to the ice core record. That's a weird number to stay constant as a fraction. It's not a thermodynamic equilibrium. Once I looked at this and oh, well, that's simple. Goes up in the atmosphere, blah, blah, blah. It's not. It turns out to be, and I don't understand this, it's a mathematical artifact of an exponentially increasing input function. It's weird. This scares me totally. Because if for some reason natural systems decided that they didn't, I mean, it's not like they're thinking, well, if they were thinking, they would have never come up with us. But anyway, it's like, why is this? And Will it stay proportional to emissions, or will it start to drop or increase? That could change everything really quickly, very quickly. What will it do in the future? Well, okay, given this nasty scenario, but we know exactly what to do. There is no problem with knowing what to do. We know, everybody knows. Okay, yeah, fruit, veg, don't drink, vote for the weed. Okay, we all know exactly what we should do, okay? But, and we meet regularly to decide this, and we have big meetings, and we feel happy. These meetings are, I can't say what I think they are, but anyway, so it goes up and it's still going up, and then we met in Kyoto, and oh, yes, sir. We met in Paris. That was a great one. Finally, everybody, okay, we got to do this. That was Paris in 2015 here. This was Paris last year when they tried to implement something that would maybe change things a little teeny itsy bitsy bit, and they got riots. So we know exactly what to do, and we're not doing it. We're not even close to doing it. So things have become desperate. Ergo, dig a hole in the ground. Okay. Even if we keep our emissions constant at today's level, which would be astounding achievement, the atmospheric concentration would still go up. If you want to, you can take home a homework assignment and return it back to me to prove this to yourself. We have to find ways of putting it back somehow, especially because we're not slowing down. And there are a wide variety of techniques, of which many of them I have absolutely no expertise whatsoever to talk to you about. I have a really difficult time growing my garden in the backyard. Not the weeds, they're great, okay, but anything useful. So I'm not gonna tell you about growing trees or putting soil back into putting carbon into soil, all those great things. Those are first order things to do, okay? We have to cut the emissions, and then there's a whole series of other things. But I'm a geologist, and a subclass of geologist known as a geochemist, so I'm gonna talk to you about what I know about. We have to put a ton back. Okay, how are we gonna do that? It's unlikely that we're gonna suck it out of the atmosphere and make big piles of coal and rebury it, okay? But we can look at the carbonate side of things, and my hero in this is Wally Broecker. Wally Broecker is an American geochemist who studied lots of different things, mainly carbon-14, and he was kind of a marine geochemist. And he tracked how those time scales and how much carbon was in the deep ocean and how it flows from the North Atlantic and sinks down and flows around and pops back up in the North Pacific, and that big conveyor belt and stuff. He had a big role in discovering and exploring that. And he was actually the one who, he wasn't the first one to say global warming, okay? That was like, you know, the first cave person who said, boy, I wish it was globally warm today. But he did publish this paper in 1975 where he predicted on the basis of some kind of hokey records that turned out to be. Anyway, what he knew was that there were exponential increasing of CO2 emissions. He kind of put things together. He said, we should have seen this already, but there were natural cycles, but we will see it when it gets to be around there or there. And what he predicted for about 2020, we have achieved. So aren't we good? Yay. Gold star for us. Oops. And this bothered him a lot, and he never let anybody get in the way of his opinion about things, to the point where he lost all his funding from the official government in the US, the National Science Foundation. They would fund just about anything except Wally, because he kind of let them know that, you know, they were, anyway, the evil empire. but he got private funding and went on with his career. And one of the things that he noted was this carbonate silicate cycle, and that it's there in the background chugging away. And so he didn't come up with the term greenhouse rock. Blame me for that. It's kind of a weird thing, but anyway. He realized that this was a natural cycle that could potentially be enhanced, sped up, perverted in some way to maybe help a little bit. Okay. Oops, geology terms. Okay, now from the next couple slides are going to have lots of weird terms. Don't worry about that. Don't worry. Okay, they're crystalline materials with chemical formulas called minerals, and the minerals come together in rocks. And geologists have just, think of it as kind of the nomenclature organic chemistry, except that it doesn't make any sense. Okay, there's two kinds of greenhouse rock. One comes in an extra heavy duty variety called peridotite. We sometimes add water to that and make serpentinite, which has serpentine minerals. And the other is what we make our houses on top of here in Dunedin called basalt. Okay, so this is the high strength. So this is hot, this is medium. Okay, two kinds of variety of those. And of course, what it has to do with is how much calcium and magnesium they have that can be chemically weathered and released and bound up in carbonate. Okay, here's a couple natural examples. You know, my ulterior motive is to show you some rocks. Okay, this is a place, okay, there's two reasons I'm showing you this. One is Andreas Weinlich visited us back in 2003 or 4 or something like that. He came for a semester from Germany and did a project, and we talked a lot, and he was having kind of an existential, what should I do with my life? And I said, just save the earth. So I don't think I really had that big an influence, but he went on and he's a world expert in this stuff. Okay, now here's where he went. He went into Norway where, oh, it's so pretty for 3 months out of the year, when beautiful, beautiful ice scraped, polished surfaces of rock. This is what geologists lust over. Me, yeah. Anyway, this is serpentinite, that's hydrated peridotite. This is something called soapstone. Okay, it makes sense, so it's not a geologic term. It's actually a soft rock, but it has some carbonate in it that's been added. And you can see it's a very sharp boundary, and that tells us that fluid flowed through the rock and reacted with it very rapidly and made this sharp reaction front. And further back, again from the soapstone, we get into a beautiful rock. Don't worry about that. This rock, all the silicate that was originally combined with the calcium and magnesium has been converted into carbonate. Now all it is this brown carbonate mineral and white quartz, which is just silica. So we went from adding water to adding some CO2 to just adding CO2. Beautiful, beautiful, 100%. Nature finds a way in the subsurface to get this reactive carbonated water down into the rock and 100% replace it. Yes, it takes a little bit of time. Okay, that's Norway. You say, yeah, okay, that's just a strange place. Let's go to the deserts of Oman. Here's a big pile of rock that's been scraped up, same kind of rock, scraped off the seafloor, plopped into the desert of Oman. It's about 100 million year old section. And we have our peridotite that's been turned into serpentine. That's the gray rock. And here is our lisbonite. This is, again, rock that has 100%, all the calcium and magnesium has been stripped from the original minerals in the serpentinite and made into carbonate, leaving quartz left over. And it's this beautiful reddish brown color because there's a little bit of iron there too. And when it gets exposed to surface, it rusts and turns nice red. And here's a close-up of that. Okay. The white is mostly silica. The brown is a fine-grained intermix of the carbonate and quartz, okay? And this is once again nature. Now, this rock looks like it's been blown up. It's all fragmented. That's not because of earthquakes. In this case, the rock has internally imploded or exploded. It's because carbonated water got into it and the reaction took place so quickly, geologically speaking, and with such force that it cracked the rock open, which allowed new fractures, which allowed the carbonated water to get further in, and this 100% replacement process take place. It's a stunning natural process. There aren't too many places where you can take rock, introduce a fluid, and change that rock over 100%. There's usually islands and stuff, not of leftover unreacted stuff, not here. Not here. This reaction is a stunningly effective reaction. Now let's stay in Oman and consider the following. Today, there's a little bit of water here and there, and some of it seeps down into the rock, and it comes back up, and it precipitates carbonate at the surface, travertine deposits. And these aren't anything really special. It's kind of that process taking place today, coming up to the surface, it degasses a little bit of CO2, crystallizes the rest of the carbonate as solid carbonate. And then around in the rock, there are these cracks and crevices and blocks and things that have carbonates in them too. And somebody did something really silly. They said, I want to know, I can see these springs forming today. There are some ancient spring deposits. I want to know how old they are. So I'm going to use a radioactive isotope of carbon, carbon-14, to date them. And then they did something really dumb, almost like a graduate student going out and collecting the wrong sample, okay? That's silly. What they did is they dated present-day travertine, ancient travertine deposits without fluid flowing, and also some of these veins and cracks. Here are the ages that they've got. Now, just don't worry about too much here, except that the presently active systems are the ones in blue here. Now, they don't have all 0 ages because the carbonate, when it goes, the solutions when they come down do dissolve some inorganic carbonate. So not all the carbon is from the atmosphere. Hence, there's some dead carbon stuck in there too, which makes the ages look abnormally old, even for presently active systems. Okay, but look, the red are these cracks and crevices that were long thought to be tens, if not 100 million years old. They're not. They have also formed recently in the near surface environment. Even here in the desert where you don't have much water, this reaction, these rocks are so reactive that the small amounts of water that flow through them are actively carbonating them. Natural systems do this reaction faster than we could do it in the laboratory. Yes, let me say that again. Nature does it faster than you could put a beaker, put some rock in it, put a sodium carbonate solution, shake it up and watch it. Amazing. Amazing. When I saw this, I said, whew, there is life in this horse hole still. Okay, that's in our one kind of carbon, greenhouse rock, the hot rock, the hot sauce variety, okay, this peridotite / serpentinite. It has lots of magnesium and calcium in it. Basalt has less, but it's still pretty good. Here we're going back up into the higher latitudes here. We're going to Iceland. Iceland's convenient because it's all basalt, It also is convenient as a source of CO2 because it turns out that the Icelanders, although they use renewable geothermal energy, some of those geothermal fluids, when they rise to the surface, actually contain dissolved CO2, which is released to the atmosphere. Oops, yeah, okay. Yeah. There's no such thing as a bad thing or a good thing, just lots of great things. Anyway, but this is going to be a perfect place to do an experiment because they have, one, infrastructure for drilling for geothermal fluids, two, point sources of fluids that contain CO2, and three, and most importantly, lots of basalt, black rock. And so it's a convenient place to do a test. It's called CarbFix. CarbFix, we don't have that yet, but we will. This was Wally Broecker's baby. He said, yeah, this is going to be good. Let's go and have a go at this. Okay, there's an idea. You get some water, you add CO2 that has been collected from the geothermal fluids. You add them together, you drill a hole, you insert this mixture down into the basalt. The basaltic rock and its minerals react, okay, and then you precipitate the released calcium, magnesium, and iron with the dissolved carbonate, and you make carbonate that lines fractures and fills voids in the rock. And you say, yeah, but those things are already there. But they injected some carbon-14 tracer, a couple other tracers. One of my favorites is sulfur hexafluoride, but anyway, let's not worry about that. And so they could figure out, is this new carbonate or is it old carbonate? And it's all new carbonate. And, oops, quote, measurements of the 95% of injected carbon had already converted. It was a huge surprise, CarbFix. Okay, amazing. Once again, field trial going faster than anybody thought. Okay, so now we get to the nitty gritty. How are we going to do this? Okay, so this is from the National Academy of Sciences and Engineering and Medicine, AKA a bunch of idiots. But no, I'm kidding about that, you know. Anyway. And this is to look at different kinds of carbon mineralization. Now, this is to be distinguished from pumping CO2 down into old oil fields and hoping it stays down there, or to the bottom of the ocean and hoping it liquefies and stays down here. This is reacting it into solid carbonate where it will survive for long time scales. So this is the amount stored per year. We need to store something out in here. There's a bunch of little, okay, what we're talking about is the in-situ on-land basalt and pertite. So in-situ on-land basalt and pertite. So we're talking about these bands down here. There's other things that you can do. You can do slag and cement waste and coal ash and all that crap, but these are the big ones, okay? Very, very, very optimistic price per ton of CO2 here, but also kind of scales of what might be possible, okay? And these guys, this isn't Greenpeace, okay? These guys actually know what they're talking about. And so, yeah, and then this is those other gaseous kinds of forms. Okay, why should we care? Because we're New Zealand and we give a shit, okay? But more importantly, we have the right stuff. This South Island is a simplified geologic map with all kinds of terminology. Do not worry about any of that. The important thing is that we have a couple of belts of rock that, when they are exposed to Earth's surface on a nice day, make beautiful outcrops of places called Red Mountain and Red Hills. And yeah, things can't grow on them. Well, there's some things can because they're kind of poisonous. They have high nickel contents. And the orange is mostly due to oxidized iron. But they are the kind of rocks, pertite, serpentinite, and basalts, and there are basalts elsewhere. We live on a big pile of basalt here in Dunedin as well. We have, all things being equal compared to the other exposed rocks in New Zealand, we have nice exposures of these things, and they're standing upright and all exposed, ready to go and do their bit. How much is their bit? How much is their bit? Oh, we should get to the scale that how much you have to do. Okay. The size of the job, I get mixed up when I convert from kilometers cubed to meters cubed and all that kind of stuff. So I'm going to keep it simple and use units of Great Pyramidness. Okay, Great Pyramid. So I've never been there, but I want to be there. But it's mostly made out of limestone. And that's one of these naturally sequestered kind of rocks. Okay, on today's Earth, which is a little bit anomalous because we don't have big shelf regions and we're killing our coral reefs. But anyway, right now, our natural marine carbonate burial flux, that's the net amount, not all of it in the ocean that precipitates because most of it redissolves, but the net amount that gets buried is about 100 Great Pyramids of limestone per year. 100 Great Pyramids. Surprisingly small amount, actually, 100 of those. Okay, Great Pyramid is 250 meters on a side and 150 meters high. If we want to get rid of that excess, that amount of CO2 emissions that nature is already not taking care of, okay, which is about half of our emissions, to offset that, we would need to bury 50 of these per year in excess of what nature is doing. 50 additional ones. 50 additional ones. That's a lot of carbonate. If I said we'd have to do it 50 times the natural burial flux, you would say that is crazy. If I said it's 50 Great Pyramids, you'd say, I don't know whether that's crazy, but it still kind of sounds crazy. And it's huge, but, okay, I'm gonna provoke you. Are you ready to get provoked? We do this stuff, we. Now, when I say we, you're saying, oh, I'm not a geologist. Okay, it turns out geologists don't dig holes in the ground. Mining engineers do. All geologists do is tell them where they could potentially dig a hole if they wanted to become rich. Okay, geologists don't get rich, mining engineers become rich. Well, actually, they don't become rich yet. Okay, the point, what is the point? Here is our Great Pyramid. These are all, you know, those whatever Google things. They're all on the same scale here. There's the Great Pyramid, 250 meters on a side. Here's McRae's, Fraser's Pit. There's the Super Pit in Kalgoorlie. It's deeper. That's why I didn't have to draw a line around it. Here's Bingham Canyon, one of the biggest holes. There's Chuquicamata, one of my favorite holes. Okay, now, yes, these have been built and dug over, in some cases, decades. It's no doubt about it. But we do a lot of this kind of stuff. We. Because after all, the stuff that's dug out of these holes doesn't just go into somebody's vault someplace. It just goes to making us have lights and cameras and all those neat things that we love having. And there's our 50 times. Now really, that's not all that much, is it? What do you think about it? Okay, now you're saying, oh, you have sold me a bill of goods and I'm not buying that for 1 minute. Okay, you don't have to. But we're gonna have to do something. Okay, this is Nature, not Nature Geoscience, not a geology journal. This is Nature, you know, top of the list, no, except for Cell. And this is what they said in July, okay? They said, to meet the goals of the Paris Climate Agreement, which, is anybody doing any of that? No, okay. Aggressive, blah, blah, but it's not sufficient, but it, blah, blah, blah. It must pursue every promising idea. This is more than a promising idea. It has been shown to work. Now, our belt of peridotite and serpentinite would be able to do what we need to do for 50 years. We could take rid of 50 years worth of the world's excess carbon emissions. We could do that for 50 years. That's assuming, of course, that everybody decides to level off at the current value, okay? What would it turn this belt of rock into? A big pile of waste rock, as we call it, big piles. We would ruin it for all time. No, we wouldn't. It's all going to get weathered away anyway. Okay? Would we sacrifice that if we knew we could do it? If we had the renewable energy to grind up the rock, to drill the rock, to obliterate it and carbonate all of it for the sake of our fellow man for the next 50 years, would we dedicate ourselves to that task? Would we? Would we? We can. Wow. Think about that, where that would put us in the old, you know, I know we're already there, anyway, top of the heap, but I have now provoked you. Thank you.